Hello everyone. Today I want to talk a little bit about light and other forms of electromagnetic radiation. So what is light? We take light for granted because we're such visually oriented creatures. Dogs get most of their information about the world through their smell, right? They also have eyes, but they get most of what they know about the world through their nose. But we are heavily dependent on our eyes. And we have very sophisticated visual systems. We can see very clearly, more clearly than most creatures, and we can see different colors of light which most animals cannot. Well, many animals cannot. But what is light? In this photo here, you see several different sources of light. There's the light bulbs that are hanging from the wire. There's a little light on her head, one of those head flashlights that you use to go into a dark place. And there's also, of course, sunlight coming from the sky, which is being produced by the sun, this enormously bright light source. So light comes from these light sources and bounces off objects, and then some of the light that bounces off these objects comes into our eyes, and that's how we can see the objects. But what is this phenomenon, light? Well, several hundred years ago, it was realized that light is a wave phenomenon. And in the 19th century, 150 years ago or so, it was realized that it's an electromagnetic wave. Now, we've talked about electric fields and magnetic fields before. An electric field is produced by a charged particle, so a proton produces an electric field. And if an electron is in that electric field, it will be affected by it. It will be attracted by the electric field of the proton. And so that's electric fields. And there's also magnetic fields. Moving charged particles produce magnetic fields that affect other moving charged particles. So for instance, the Earth, its core produces a magnetic field because of the moving charged particles in there. And that huge magnetic field that the Earth produces deflects charged particles, moving charged particles away from the Earth, protecting the atmosphere. So there's two types of fields that collectively are called electromagnetic fields. Well, it turns out that a changing electric field produces a magnetic field, and a changing magnetic field produces an electric field. So in this diagram, you see the blue electric field lines designated by E, and the red magnetic field lines designated by B. So as these fields change, the changing electric field produces a magnetic field, which changes, producing an electric field, which changes. So electromagnetic radiation propagates through space because of these interacting fields. So this was realized in about 1850, that light is an electromagnetic wave. It was understood earlier than that, though, that light is a wave, because it displays different behaviors that waves are known to exhibit. So for instance, in this picture, this guy is making waves on water. He's got these two balls connected to some wires, and he's oscillating the one ball up and down, which makes these waves that are propagating away from him in these circular shape. Now he's only making waves with one of the balls here, but in the next picture he's making waves with both of the balls, and you can see that the two ring-shaped sets of waves are propagating out, and they interact with each other, and you have what's called wave interference. So where the peak of waves from one ball meets the peak of waves from another ball, you have the two waves sort of add up and you get a taller wave. That's right here. And where the peak of one wave meets the trough of the other wave, the low point, then you get the water is kind of flat because a peak added to a trough gives you a zero wave. This is called wave interference. Constructive interference where they add, and destructive interference where they subtract. This is a characteristic of all waves. They interfere with each other like this. And this phenomenon was observed with light waves as long as a couple hundred years ago. And here is light going through, it's gone through two narrow slits, so it's sort of like the two sources that that guy was producing on the water, but these are electromagnetic waves. And instead of the light making a pattern of two slits, because it's traveling through the two slits, it makes a much more complicated pattern, something like the pattern that was on there, the alternating tall waves and short waves. Here it's alternating bright and dark places because we're talking about light. So light is definitely a wave, but it was also realized around the turn of the 20th century in 1905 that light is a particle. So it's a particle called a photon that acts as though it rides on a wave. So it's like surfing on these unseen waves, these waves that really don't exist. And you can see that it's a particle. Here's that same double slit experiment in a different color light. And up here, there's just a few photons have come from the light source, and you can't really see the pattern, but the more and more photons come in, the more distinct the pattern becomes. So when you get down here, it looks very much like it's a wave, but at first you can tell that it's a particle in that way. So it's a particle that behaves as though it's riding on a wave. And this is actually true of all the particles that make up the stuff in the universe, including protons and neutrons and electrons. If you remember from when we were talking about electron orbitals, I talked about the orbitals as though they were these kind of standing waves that are oscillating around the nucleus of the atom. And the different wave forms are the different orbitals that electrons occupy. So the electron itself takes on this wave-like form. So all particles have a wave-like nature. It's just more obvious with light than it is with the matter particles that they're waves. Now, I also want to talk about different wavelengths of light, and in order to do that, let me define wavelength. So at the top here, you see this is just generalized wave form here. The wavelength is the distance between two consecutive peaks of the wave. So imagine an electromagnetic wave moving through space. It's the distance between two consecutive peaks. So, and there's a huge range of wavelengths that photons come in. Now, I also want to talk about wave frequency. The frequency of a wave, any kind of wave, is the number of wave peaks that pass a point in 1 second. So down below you see two waves. Let's say they're traveling at the same speed. The top one has a longer wavelength, but the bottom one is going to have a higher wave frequency because you see more of those peaks are going to pass a point in 1 second. That's what's meant by frequency. And we'll see that there's a broad range of frequencies that electromagnetic waves come in. Okay, so you can, with light, you can talk about either the wavelength or the frequency. The longer the wavelength, the shorter the wave frequencies. And let me show you a diagram of the whole electromagnetic spectrum of light. The spectrum is the whole range of wavelengths that light comes in. You can talk about the spectrum of a single light source, how much of each wavelength is in that wave source. So this is a pretty complicated diagram, but in the middle you see the names of different wavelength ranges of electromagnetic waves. There's radio waves, which you've certainly heard of, microwaves, infrared, visible, that's the wavelength range that we can see. You can see it's relatively narrow. Ultraviolet, soft X-rays, hard X-rays, and gamma rays. Now you may have heard of some of those terms before and not realize that they refer to a similar physical phenomena. The only difference between these ranges is the wavelength. And there's a very large range of wavelengths. Look up here at wavelength. 10 to the 3 meters, 1,000 meters, 1 kilometer. That's 0.6 miles. Radio waves can have very long wavelengths. That is the distance between consecutive peaks of the wave. Here's 100 meters. The radio waves go down to about 1/10 of a meter. That is about 10 centimeters, that far. And then below that, you talk about, they call them microwaves, from 1/10 of a meter to about 1/10,000th of a meter. Those are called microwaves. Micro because they're smaller than most radio waves, but much longer than other parts of the spectrum. And then you've certainly heard of infrared waves before, so from about 1,000th of a meter up to the visible range, 1,000,000th of a meter. That's called infrared radiation. And then there's the narrow range that we can see. It's around about 1,000,000th meter wavelength. That's the typical wavelengths that we can see. And we can see a narrow range of them. And you may notice that there's a rainbow of colors in there. The different colors of light that we see are different wavelengths. So our eyes have wavelength sensitivity. Red is the longer wavelength, blue is the shorter wavelength. And then there's ultraviolet, shorter wavelength than that. X-rays, so when you get an X-ray at the doctor, they're sending these very short wavelength waves through your body because your skin happens to be transparent to them. And then there's hard X-rays, even shorter wavelength, and then gamma rays, the shortest wavelength electromagnetic radiation. Now, as I said, the longer the wavelength, the lower the wave frequency, right? So you can also talk about the frequency of radio waves, right? Those are very low frequency electromagnetic waves. Microwaves have higher frequency, infrared have higher than that, visible higher than that, and the highest frequency waves are gamma rays. Now, look at the wavelength of gamma rays. They go down to about 1/1,000,000th of a meter. So that's, what, a quadrillion times shorter in wavelength, a quadrillion times higher in frequency than the longest radio waves. So there's a huge range of wavelengths that electromagnetic radiation comes in. And again, these are all photons that behave as though they are moving on these waves. They display all this wave-like behavior. Now, what does the wavelength of a photon have to do with the photon itself? Well, it turns out that the higher the frequency of the wave, electromagnetic radiation, the more energy is in each photon that's involved. So this bottom graph shows the energy of a photon. So over on here, gamma rays, a typical gamma ray photon has 1,000,000, the unit of energy is called the electron volt. It's a unit of energy they use in physics, 1,000,000 electron volts. And then down to the lowest energy radio photons, about 1,000,000th of an electron volt. So the highest energy photons are the shortest wavelength, move as though they're on the shortest wavelength waves. Visible light is around 1 eV per photon. So the light that we can see is about in the mid-range. Okay, so now, what the different light sources that produce different energy ranges? Not surprisingly, the hotter an object is, the higher the energy photons it tends to produce. So there are very extremely energetic phenomena out there in the universe that produce gamma rays, very, very high energy photons. And then there's cooler substances that produce X-rays, and then ultraviolet. The sun is right in the middle. Its surface temperature is about 6,000 Celsius, or about 9,000 Fahrenheit. It produces visible light. At cooler temperatures, like the surface of a human being, we produce infrared radiation, even cooler, that produce lower and lower frequencies. Now, so the coolest objects in the universe produce the lowest frequency photons, the lowest energy photons. Now, radio waves are also produced artificially, right? So one of the things that produces radio wave, I don't have my cell phone with me, but cell phones communicate by producing radiation, which is picked up by a cell tower that is near you. That carries the signal of your voice with it. People have learned how to artificially produce these lower frequency radio waves, and that has helped us to communicate. And in fact, most of that radio wave spectrum, and actually into the microwave spectrum, is utilized in communication. But different frequencies, like cell phones use different frequencies from police radios, which use different frequencies from from air traffic controller radios and so forth. So people have figured out how to artificially produce these low frequency waves, and we can use them to communicate. Now, what's another thing that's shown here is a microwave oven. Microwave ovens produce waves at about 10 to the 9 waves per second, and that is strongly absorbed by water. So in a microwave oven, there's loads of that radiation being produced and absorbed by water, and that's how those things work. Okay, so there's the spectrum of electromagnetic radiation. Here's an example of emission from human beings and other objects that are similar to us in temperature. This is an infrared, what they call a thermal infrared photo of people getting on and off a subway train, and you can see that this guy's face is brighter than the train because his face is actually warmer than the surface of that train. So places that are brighter on here are places that are warmer. Notice the wheels of the train are bright because they've been working. The train's been rolling, and energy from the motor and friction with the track has caused the wheels to be hotter. And so this was what the world would look like to you if you could see in the thermal infrared range, which is about a factor of 20 lower in frequency than the visible light that we can see. So here's an example of something in the infrared part. And you can actually buy an infrared camera these days that is sensitive to thermal infrared. You can get little cameras that'll plug into your cell phone and use the screen of the cell phone to display it, but just the camera is sensitive to the thermal infrared, so you can look at pictures, like you can point it at something and see the radiation coming from it. So this is radiation that we're emitting, right? When we look at each other, is that radiation being emitted by the person? No, that's reflected light coming from a hotter source, like the sun, or the gas in a fluorescent light bulb, or the filament in an incandescent light bulb. All right, this is the sun, believe it or not, taken in extreme ultraviolet. So this is higher frequency than the visible light that it produces. Now, you might notice that the surface of the sun, it looks kind of dark, but the emission in these higher frequencies is coming from above the surface. The sun mostly emits visible light on its surface, but above the surface in its atmosphere, the gas is hotter than it is on the surface, and so produces higher frequency radiation. And this is coming from that. These loops are loops of magnetic field line. The sun also produces strong magnetic field, and that is thought to be what heats the atmosphere and makes it glow like this. This graph just shows you the opacity of the Earth's atmosphere as a function of wavelength. So 100% means that the Earth's atmosphere is completely opaque to those frequencies. Okay, and this is listed in wavelength here. So it's short wavelengths. So like gamma, X-ray, ultraviolet. The atmosphere is 100% opaque. So we can't see the sun in extreme ultraviolet. That picture was taken by a telescope that's in space, that was put into space on a rocket. But you can see, as you get to the visible part of the spectrum, this rainbow is the visible light. The opacity of the atmosphere decreases, and there's a narrow, what they call a window, in which the atmosphere is almost completely transparent. In other words, the opacity is very low. But it's opaque in most frequencies, but it's quite transparent in a long range of the radio part of the spectrum. This is why we can communicate with radio frequencies, because the atmosphere, they travel freely through the atmosphere. But different substances are opaque to some frequencies and transparent to other frequencies. So for instance, I can make a cell phone call from in here, right? Because the walls are transparent to radio frequencies, but they're opaque to visible frequencies, right? But on the and let's see, X-rays, according to this graph, the Earth's atmosphere is opaque to X-rays, so we can't see the sun in X-rays, but it's transparent to visible light. But on the other hand, your skin is transparent to X-rays, but opaque to visible light, right? I can't see through my hand, but you can get an X-ray because the skin happens to be transparent to X-rays. So different substances are opaque to some frequencies and transparent to other frequencies. So there's just a little bit about light.